The quality of life at Simon Fraser University in Vancouver is plain to see, but behind the smiles lies a world-class math department.
I would describe the math department at Simon Fraser as collaborative, innovative, enthusiastic and dynamic. We focus on areas of strength. I think we're very good in those areas. And our connecting theme is computation. I think what's also interesting about this department is really a fairly large group of faculty on the applied side of mathematics.
Those applications are making a real difference to the Vancouver community, not least at St. Paul's Hospital through the work on a form of functional medical imaging called dynamic SPECT.
In SPECT, the way it works is we administer a radioactive tracer to the patient, and then the camera slowly rotates around them and detects the radiation being emitted by that tracer. Medical imaging is a very interdisciplinary field, and obviously in nuclear medicine there's lots of physics, chemistry, and biology that goes into it. Where the math really comes in is the reconstruction of a three-dimensional object from these two-dimensional views that the camera takes from around the patient. And basically without mathematical imaging reconstruction techniques, all that we would be able to do is get two-dimensional views. So it's basically the difference between having an X-ray of a patient and having a CT scan, which gives you the full 3D information. If you really want to know if your method is going to work, you have to try it on real-life data, and that's what our collaboration with St. Paul's has allowed us to do.
When you're in applied mathematics, you want to solve problems which are relevant, so you'll have to talk to the people who know about these problems. So you will work with engineers, with people from industry, with people from other sectors. I think we enjoy that sort of collaboration.
One such partner is Oral Systems, which creates chemical process simulation software. They reached out to SFU to work on truly groundbreaking projects.
One of the things we're trying to do is, if you picture how the chess game is played by a computer, we want to do that with a chemical process, trying to play the process and see what the next best move is. Unlike a chess game, all the moves are very defined. In a chemical process, nothing is defined, and so the mathematics of it gets very strange and hairy, and those are the kinds of things that we're trying to develop, and largely our approach is very novel. I don't think there's anybody else in the world that's really working on what we're working on, so there's times when we do need to have the smarts of mathematical department behind us.
Collaboration isn't just about finding partners in industry, it's about utilising the different skills people have within the university. Nalima Nigam is a mathematician, and she's working with a specialist in muscles and human movement.
My muscle project is in collaboration with James Wakeling, and we're interested in why do muscles bulge? And is there a simple mathematical way to explain just this simple observation? When you flex your arm, you feel your muscle bulge. Why? We know this, but we've never explained it properly. That's our goal.
The internal structure of the muscle is very complex. There's many fibers. They all follow curved paths through the muscle. There's build-up of pressure within the muscle. So the computational side is complex, and then actually mathematically how to code the models is a complex task. So as yet, people haven't really made a complete continuum model of muscle which contains some of the pronation angles involved. And this very much needs the expertise of the mathematicians at this institution.
I like to work following my scientific curiosity, and to do it in collaboration with a scientist is essential. I could sit at my desk and do it all alone, but that would be hardly any fun. I'm not a kinesiologist. James brought this really interesting problem and a wealth of experience in kinesiology, and I bring to the table something that comes from mathematics. So together, this is a fun project. Alone, it would be boring.
At Simon Fraser University, there is a sense that no problem is too big, and by working together, anything can be achieved.
I think Simon Fraser is a university which it's a place where when you have a new idea, you will get a lot of support. People will say, well, let's try this. So there's a very good spirit in that way. So I think that's something quite special about this place.